When we read standard chemical formulas like H2O or NaCl, we get a basic parts list. But those letters and numbers hide a crucial detail: how those individual atoms actually lock together in three-dimensional space. To find out, we use a tool called a Lewis structure. A Lewis structure is a visual map that shows exactly how atoms share electrons to stay together. Drawing an accurate one requires a strict 5-step protocol. Before we begin, you need a few physical tools. Grab a piece of paper, a pencil with a good eraser, and a standard periodic table. By physically drafting these diagrams, you can predict exactly how a molecule will behave, react, and bond, which saves you from having to rote memorize hundreds of individual formulas. Step 1. Determine the molecular compound's total electron budget. To do this, we count the valence electrons. Valence electrons are the outermost electrons that an atom actively uses to form bonds. On the periodic table, valence electrons match the group number 1 through 8. For hydrogen sulfide, or H2S, our equation shows 2 hydrogen atoms bringing 1 electron each, plus 1 group 6 sulfur bringing 6. This is a strict budget of 8 total valence electrons. Step 2. Arrange the atoms to form a skeleton structure. You need to identify your central atom, which sits in the middle, and the terminal atoms, which surround it. When making this choice, there is one unbreakable rule. Hydrogen is always a terminal atom. It can never be placed in the center. Because of that rule, we place sulfur in the center. Next, we flank it with the 2 hydrogen atoms and connect each terminal atom to the center using single lines. These lines represent our first chemical bonds. This skeleton gives us the physical layout of H2S. However, it does not yet account for the total budget of 8 electrons we calculated in Step 1. Step 3 is to satisfy the terminal atoms. We do this by adding lone pairs, which are simply non-bonding pairs of valence electrons, to the outer atoms until each has exactly 8 electrons. But there is a major exception to the standard rules. Hydrogen structural requirements are much lower. It only needs 2 electrons to be perfectly stable. Notice these pulsing lines in our H2S diagram. Each single bond we drew already represents 2 shared electrons. That means our hydrogen atoms are fully satisfied by the skeleton alone. We add no extra electrons to them. That brings us to Step 4, allocating any remaining electrons from our initial budget directly onto the central atom. Let's check our budget math. We started with 8 total electrons and spent exactly 4 on those 2 single bonds, leaving exactly 4 to distribute. We place these 4 remaining electrons as 2 distinct lone pairs directly onto the central sulfur atom. Electron distribution is a strict zero-sum process. Every electron from your starting budget must have a specific assigned location on your map. Step 5 is the final inspection, checking the central atom against the octet rule. The octet rule states that atoms prefer to be surrounded by exactly 8 electrons. Looking at the central sulfur atom, we tally its resources. It has 4 electrons from the 2 blue bonds, plus 4 from the 2 red lone pairs, totaling exactly 8. It meets the octet rule. Our H2S structural blueprint is officially complete. But sometimes you will run into a critical failure condition. You will deplete your entire electron budget, but your central atom will still have fewer than 8 electrons. When this happens, you must fix the deficit by moving electrons. Specifically, you take a lone pair from a terminal atom and convert it into a multiple bond. To fix a failing molecule's deficit, we erase a lone pair from the outer atom, slide those electrons into the gap, and draw a second blue line, creating a double bond. These shared electrons now count toward both adjacent atoms' octets simultaneously. Multiple bonds are nature's structural compromise. They maintain chemical stability even when a molecule's available electron resources are severely limited. By following this process, you have successfully engineered a tangible, physically accurate map from a seemingly random string of letters and numbers. This finished diagram provides immediate physical data. You can now clearly identify the central atom, the terminal atoms, the exact locations of the bonding pairs, and the placement of the non-bonding lone pairs. Now it is your turn to apply this exact framework. Grab your worksheet and run the 5-step protocol on the remaining examples: HCl, CH4, and NAF. Trust the rigid rules of the protocol. If you count your budget carefully and satisfy your octets, There is no molecular architecture you cannot decode and map. Mastering Lewis structures is how you stop simply reading about the rules of chemistry and start actually building it from the ground up.